In this video, we're going to solve a first order RC circuit that has two different sources involved in it. So our standard process, as we've seen, to solve these first order circuits is to look at what happens before the switch happens, what happens after the switch happens, and what happens as you go to infinity. Lastly, you find the time constant and you put all of that together to write your answer. Now, on this one, we are looking for the voltage across the capacitor, and we need to see what happens before the switch changes. So in this particular problem, the switch starts closed and then opens. So while it is currently closed at 0 minus, we're going to have a circuit that is in steady state position. What that means is our capacitor is going to become an open. And then we need to find the value of the voltage across the capacitor before the switch happens. Now, we can go ahead and maybe use node voltage here. We'll call this, say, V. So current going left would be V minus 9 over 6K. The current going left and down would be V minus 0 over 6K. The current going right and down, V minus 0 over 6K. And then the current going down on the far right is really negative 2 milliamps. We can clear out our denominators by multiplying by 6K. And then we combine together, we're going to have 3 V's here. And then minus 21 is going to be 21 volts over there. So V is 7 volts. I'll stylize this V so you can tell the difference between the variable and volts here. So that means the value of the voltage across the capacitor before the switch changes is 7 volts. If I look at what happens immediately after the switch opens up, so once this switch opens up at t equals 0, there's no longer connection there. That means the stuff that's going on this circuit on the left is going to be completely separate from the stuff on the circuit on the right over here. So we're going to go ahead and just draw the right side. We have our capacitor. We have 6 kiloohms. And then we have 2 milliamps here. And since it's the voltage across the capacitor that doesn't change instantaneously, it was 7 volts before the switch happens. It's still going to be 7 volts after the switch happens. And since we are actually looking to find that, not some other voltage or some other current, we can just go ahead and write down then V0 of 0 plus is 7 volts. Now we need to look at what happens as you go to infinity here. So that means it's infinity, the switch has already happened, and we're in steady state again. So the capacitor becomes an open, and we have this here. And if I want to find what is the value of this voltage here at infinity, well, in this case, all this 2 milliamps of current is going to go through the 6 kilo ohm resistor. So by Ohm's law, V0 of infinity is in parallel to that is 6 kilo ohms times 2 milliamps. So it's going to be 12 volts. Last thing we need to do is figure out our time constant here. So it's important to note that the time constant is for the part after the switch happens. After the switch happens, you can either look at the 0 plus circuit or the infinity circuit and ask yourself, what is the R Thevenin from those two nodes at the capacitor? Well, an independent source is not going to affect the R Thevenin, so we just have the resistor there. So R Thevenin is just 6 kiloohms, which means my time constant, which is R Thevenin C, is going to be 6 kiloohms times the capacitor, which in this case is a 2.5 microfarads capacitor. And so that's going to be a 15 millisecond time constant. So we know our answer is going to be x of t is k1 plus k2 e to the negative t over tau. The function we're looking for here is v0 of t, k1 plus k2 e to the negative t over tau. We know if you plug in infinity, it's going to work out to be 12 volts. Plugging in infinity gives you your k1. We know if you plug in 0, you're going to get k1 plus k2, and plugging in 0 is supposed to be 7. So k2 is negative 5, which means our final answer then is v0 of t is 12 minus 5 e to the negative t over tau. Tau is 15 milliseconds or 0.015 seconds. And this is all in volts. And so there is the answer to our first order circuit.